Okay, so let's jump right in. Imagine you're standing in front of this enormous machine, and it's covered in literally millions of tiny knobs. Your job is to tune every single one of them perfectly to get the machine to work. How on earth would you even start? Which knobs do you turn? Which direction? It sounds completely impossible, right? Well, that's pretty much the core challenge that machine learning has to solve every single day. And that's the big question we're going to tackle in this explainer. It's not about just guessing or randomly twisting things. No, it's about a really systematic, honestly a brilliant process that's powered by two core algorithms. And together, these two things are the engine that drives basically all of modern machine learning, from the Face ID on your phone to these massive language models that are changing everything. At the end of the day, what we're really talking about is a giant puzzle. It's an optimization puzzle. We have a model, it makes mistakes, and our goal is to find the absolute best settings for all its parameters, all those knobs, to get those mistakes as close to zero as possible. And this is where our two heroes, gradient descent and backpropagation, come into the picture. Now, you might think these are brand new ideas, but they've actually been developing for a long time. I mean, the basic idea of steepest descent goes all the way back to 1847. And the math for what we now call backpropagation, that was actually figured out in 1970. But the big bang moment was in 1986, when a landmark paper showed just how powerful this could be for training neural networks. That's when things really took off. So let's start with the first piece of this puzzle: gradient descent. Honestly, the best way to think about it is as our compass. Imagine you're lost in a thick fog on a mountain, and you just want to get to the bottom. Your compass tells you which way is down. Gradient descent does the exact same thing for our model. It tells it which direction is downhill towards fewer mistakes. I love this quote because it just nails the concept. The loss of our model, how wrong it is, that's like the elevation. The settings of all those millions of parameters, that's our exact location on this landscape. All we want to do is find the lowest possible valley, the point with the least error. And gradient descent is the algorithm that, from wherever we're standing, points out the absolute steepest way down. So what's really going on under the hood? It's a loop. It's an iterative process. First, it calculates something called the gradient. That's just a fancy word for the direction of steepest ascent. Then, it nudges all our parameters in the opposite direction. Why opposite? Well, the gradient points uphill, and we want to go downhill. And it just does this again and again and again, taking little baby steps towards the bottom. Okay, I know math formulas can look a little scary, but stick with me because this is way simpler than it looks. It's just a set of instructions. It says our new parameter settings are just our old settings minus a small step in the downhill direction. That step is controlled by two things. That little eta symbol is our learning rate, think of it as our step size, and that triangle thing is the gradient, which tells us the direction. We subtract it to go down. That's it. That's the entire instruction for every step. So the whole dance boils down to this super simple, repeatable loop. Step 1, figure out which way is down. Step 2, take a little step that way. Step 3, repeat the whole thing from your new spot. You just keep on doing that until the ground pretty much flattens out, which means you've hit the bottom of a valley, a point where the error is minimal. All right, so gradient descent is our compass. It tells us which way is down. But in a model with millions of parameters, how do we even calculate that direction? How do we know how much turning each individual knob contributes to the final error? That's where our second algorithm, backpropagation, comes in. If gradient descent is the compass, backpropagation is the one that makes the map. The whole job of backpropagation is to compute that gradient, that downhill direction, for every single parameter in the network, and to do it efficiently. It does this with a really clever trick. It applies the chain rule from calculus, but it works backwards. It starts from the final error and pushes that error back through all the layers, figuring out who's to blame along the way. People sometimes talk about backpropagation like it's some kind of black magic, but it's really not. At its heart, it is just the chain rule, something you probably learned in a high school calculus class. The absolute genius of it is how it organizes the calculation to avoid doing the same work over and over again, making it possible to train these gigantic models we have today. And this slide really shows you how efficient it is. The cost, the amount of computation it takes to get the gradient for all the parameters, which we call O of P, is roughly the same as the cost of just making one single prediction in the first place. That efficiency is, and I'm not exaggerating, the reason modern deep learning is even possible. So let's move from all this theory to what it actually looks like in practice. We'll check out how the complexity changes and how these big ideas actually get boiled down into just a couple lines of code. For a really simple model, like a basic linear regression, the time it takes to calculate the gradient is mostly about how much data you have. But for a big neural network, it's more about how many parameters there are. And look at the space complexity. That's memory. For a neural net, you have to save the outputs of each layer, the activations, as you go forward, so you have them handy for the backward pass. It's a crucial detail.
And after all that calculus, after backpropagation does all the heavy lifting of figuring out the gradients for millions of parameters, the actual update, the step downhill, boils down to this one beautiful, simple line of code. You take your weight and you just subtract a tiny amount in the direction of the gradient. That's it. That's the learning.
Okay, so here's a really important question. Does this process always find the absolute best, perfect solution? Well, for simple problems that are convex, meaning their error landscape is just one big, smooth bowl, then yes, you're guaranteed to find the bottom. But deep learning is non-convex. The landscape is full of tons of hills and valleys and weird ridges, so you're only guaranteed to find a minimum, which might just be a little local ditch, not the deepest canyon on the map. So why does all this matter so much? Because if you're ever in a technical interview for a machine learning job, these concepts aren't just trivia. They are the absolute bedrock of the entire field, and being able to explain them clearly is a massive, massive signal that you actually know what you're talking about. A good interviewer won't just ask you for a definition. They're going to ask you about the implications. They'll want to hear you explain why Backprop is so efficient or why you have to cache those activations. They'll want you to discuss the trade-offs of choosing a learning rate or the differences between the various flavors of gradient descent. And speaking of those flavors, there are three main types. You've got batch, which is super accurate because it looks at all your data for every single step, but it's painfully slow. Then you have stochastic, which is super fast because it just looks at one example at a time, but it can be kind of noisy and jumpy. And right in the middle, you have mini batch, which is the happy medium that pretty much everyone uses today. It's a great balance of speed and stability. And of course, the story doesn't stop there. People have built even smarter optimizers on top of this foundation. You've got things like Momentum, which helps you roll past small bumps, or Atom, which is really clever and adapts the learning rate for every single parameter. They're all still just gradient descent, but with some extra tricks to help navigate that crazy landscape better. So if you only remember one thing from this whole explainer, let it be this. This quote sums it up perfectly. Gradient descent is the strategy. Our big plan is to always walk downhill, and backpropagation is the tactic. It's the brilliant, efficient method we use to figure out which way downhill actually is at every step of the journey. And that leaves us with the final big thought. This whole process is amazing at finding a nearby valley, a spot where the error is low. But in the unbelievably vast and complex landscape of deep learning, how can we ever really be sure that the valley we found is actually the deepest one out there? And that, right there, is one of the biggest unanswered questions in the field, and it's what keeps things so interesting.